here's why this topic comes up now. Let's take an example. Okay, solve. Okay. So let's get all iPods and all that stuff, everything put away. No distractions, go and get rid of that. There you go. So what do we do to solve this? What are the 2 steps in, or 3 steps in order to solve for x? Subtract 10, divide by 3, square root. Okay, good. So let's do that. So subtract 10, no problem. Divide by 3. Do you see an issue coming on here that's going to cause problems for us? Negative. Yeah, we're taking a square root of a negative number, right? So what do we do with that, right? How are we going to deal with that? Okay, we need the imaginary unit. In fact, if I go back a little bit, does everybody see here that I'm going to do one more step that wasn't included that might be useful? Might does this. Okay, what if we, one more step, so we end up with x equals, now what do I need? If I square root both sides of an equation, I can't forget to include plus or minus. Good. Okay, so I need plus or minus the square root of negative 12. Now we have some properties of square roots, right? We know that for square roots we can say this. The square root of the product a times b simplifies to what? Square root a, square root b. Good. So the square root of a product equals the product of the square roots. That make sense? Yeah. Okay? So in this case, that's helpful because we can write this as the square root of 12, which we can simplify, right? Times something that's a little problematic. Square root of negative 1, right? And so, what do we do? Problems. All right, so here's what we do. We introduce what's called the imaginary unit. Unit just means 1. Okay. So we've always been told that you can't take the square root of a negative number. True for real numbers. The result, if you do that, is a number. It's just not what we call a real number. It's what we call instead an imaginary number. Okay. Now, before I go any further, too, I want to say something about that. This is an unfortunate choice of terms to describe this stuff because it somehow indicates that real numbers, the kind we've always dealt with, are somehow better than these weird things called imaginary numbers, which can't exist because they're imaginary. Not true at all. Imaginary numbers are just different. They're no less valuable. They're just different. Real numbers are numbers that are used for things like counting. Imaginary numbers are just used for different things. But in my career as a physicist and an engineer, imaginary numbers play just as important, if not a more important role than real numbers. There are things you can do with imaginary numbers that are amazing. For example, if you are, let's say you're an electrical engineer, and you need to, if you are in circuit design, let's say you're working on developing chips, integrated circuits. Okay, one thing you have to do is you have to know very precisely what kind of an impedance load any electrical component is going to place in a circuit. Impedance is just a fancy name for how much resistance is there to pushing current through the circuit. Okay, that's all. Those are all really critical numbers that you got to know about in calculating impedances for circuits. And this is all probably sounds a little strange to you, but impedances, if you want to do this easily, impedances are all defined in terms of imaginary numbers. So when you're calculating complex impedances, you just add those numbers up as complex numbers, and it's really easy to do that way. You can do it in a way that doesn't use imaginary numbers, but it's very difficult. There are other things you can do too. I'll give you one quick example that I just remember from college. This always really impressed me. If you take something, I don't want to spend too much time on this, but it's kind of, you'll like this. If you take something like fluid flow through a pipe, okay, so here's our pipe, let's say it's gonna go around a bend. Okay. When you're trying to approximate, and that's really, my background is in physics, and so what physics is really all about is building models that describe, mathematical models that describe the way the universe works. Well, one nice, efficient model for fluid flow it's called laminar flow. And the way you gotta think about laminar flow is if you look at the flow of water through a pipe, so if we looked at, like, here's our pipe in cross section, so if there's the pipe coming at us, you can think of the water as being divided into concentric cylinders, just like, when you're in the recycling bin, when you take the tin cans and the bigger ones go on the outside and the smaller ones go in the middle and you nest the cans like that. That's what I mean by concentric cylinders, right? A concentric cylindrical shell. So on the outside, we've got this layer of water that we'll just color it blue. Next to that, there's going to be another layer of water that we'll color orange, etc., all the way down, so on and so forth, to that middle layer of water, which is like the lead in a pencil, okay, which just sits in the middle. Now, when we do the calculus, which you'll eventually be doing, we treat these layers as though they have infinitely small thickness, and we just add up an infinite number of them. But for the sake of discussion, we don't have to do that. We'll just say that we'll just divide them into these little thin concentric shells of water. Why is that useful? Well, I want you to think about the flow of water for a second. Where would you expect the water to go the fastest in the pipe, and why? In the middle. Okay, right. How come? Say it again. Least resistance. Where would it go the slowest, conversely? On the outside, because there's some friction against the outside of the can. Does that make sense? And so what laminar flow, that model says, is, well, let's just treat, if we want to get the dynamics of the water, let's just think about these concentric layers as having slightly different velocities. The inside one is going to slip through the pipe a little faster than the one next to it, and the slowest one is that outside shell of water. Make sense? Okay, that works really well until you go around a bend. When you go around a bend, you have problems, right? What's going to happen? So what's going to happen to the water when you go around a bend? What do you think? Is it gonna wrap around the corner real nicely? Doesn't, does it? Now, let me ask you something. If you catch a baseball that's thrown at 80 miles an hour compared to one that's thrown at 25 miles an hour, which one is gonna hurt more? 80? Which one are you gonna feel more recoil from? Yeah, catching 25 is just going to be kind of like that, but 80, it's going to take your hand and move it back a little bit, right? There's a little more momentum associated with that. Another physics term. Momentum just has to do with mass times velocity, times speed, right? All of the little water particles essentially have the same mass, but the ones that are flowing down the middle of the pipe have more velocity, don't they? Right? And so those guys in the middle, when they make that bend, their momentum is going to carry them forward more forcefully than the particles on the outside, right? Does that make sense? And so these guys are going to get pushed towards the outside of the pipe. As they do that, they're going to displace the water particles on the outside, and you get this turbulent flow, which is complicated. Okay, now it's really difficult to model turbulence because it's an inherently chaotic environment. But there are some ways you can do this. This was really cool. Now, it's not perfect, but you can, by making what's called some conformal mapping and taking this right angle bend in the pipe and mapping that into the complex plane very carefully, and we'll talk about what that means. Complex plane is just like an XY plane. You can straighten out the pipe, and you can trade it for a situation where the pipe is now straight. The space in which it's straight is a little bit weird, but now that center particle just moves straight down the pipe, and it ends up at some location down here after some amount of time. And let's say that the curve in the pipe was actually there. Well, you can figure out what the velocity is in the position and all the parameters of that particle. And then you can go back up to the straight pipe and say, okay, let's remap that back into the regular XY plane with real numbers. And it tells us roughly where this thing is down the pipe, what direction it's going, how fast it's going. So I don't know if that makes a huge impression on you, but man, that's pretty cool. I mean, there are some things you can do with complex numbers, with imaginary numbers, this imaginary unit that are really, you just have no idea yet, but you will, hopefully, someday, if you keep studying math, which you're all going to do. All right, so back to business. So this is a big deal. These numbers are important. Just because they're called imaginary doesn't mean they're any less important. They're just different. That's it. Okay? All right, so let's just talk about these a little bit. So the imaginary unit, we give the symbol I, and usually it's a cursive I, like a script I. Okay? Now the definition of I is that it's just equal to the square root of -1, which we already know is undefined for real numbers. Okay? So, excuse me. Let's just take that and go with it a little bit to talk about some properties of square roots of negative numbers. So if r is a positive real number, then we can always say, so r is positive, then the square root of -r is negative, right? We can always break that up into the square root of r times the square root of -1, right? Does that make sense? Back to our example. Oops. Where is our example? Oh. Well, I guess it wasn't on there. Let's make one real quick. I want to show you how we finish this up. I think our example looks something like this. Didn't we end up with an answer being x equals plus or minus the square root of 12 times the square root of -1, right? We split it up that way because we started off with x equals plus or minus the square root of -12, and we broke that up into the positive 12 and the -1, right? What is this going to become then? That's I. And so our answer would look like plus or minus the square root of 12 times I in our last example. Okay? And that means something. That means that's an imaginary number. It's got an I in it. Anytime we have an I in it, it means it's got this imaginary unit, and therefore, taken as a whole, this represents two different imaginary numbers that are both solutions. Okay? Well, it won't be. As you do a few of these, it won't be.
But why?
Because we want to know what the answer to that problem is, right? We had this original algebra problem right here, and we wanted to know the answer to that thing, right? What is x equal to? We got stopped. We got stopped when we got, when we got there, because we had a negative number. Well, what if we don't want to stop? We want to know, what is that answer? It does have an answer. It just doesn't have a real number answer. So if we want the answer, we have to use the imaginary numbers, because our answer is imaginary. Right? So our answer ended up looking like x equals plus or minus, and I can simplify the square root of 12, but I'm not even going to worry about that part now. This is the part I'm interested in, is that I. Okay? Does that make sense, why we're doing this? Because we want to be able to answer that question. Okay, so let's take some examples. How would we rewrite the square root of -3 then? Yeah. Okay, I times the square root of 3. Why do we put the I first? Only reason we do that is if the I is afterwards, the question is it inside the radical or outside of the radical? It's hard to tell. So we just put the I in front, just so we know for sure it's not. How about this one? Okay, but what is the square root of 4? 2. Yeah. Okay, so that one's 2i. Now we can put the I afterwards because there's no radical there, and so we don't need to worry about confusing whether the I is inside or outside the radical, right? Okay. So if I equals the square root of -1, then what's I squared equal to? No. If I equals the square root of -1, what's I squared equal to? Well, what does a squared do to a square root? Cancels it. So it's -1. Yeah. Right? Make sense?
Yeah.
Okay, let's for a second, before we go any further with the algebra, let's just kind of get used to the idea of these i's and how we deal with them. What if we had other powers of I? What about I cubed? How can we deal with I cubed? Any suggestions? If it's I cubed, remember, I can break that up into different powers of I that are multiplied together, right? Product of different powers. What if I broke it up into an I squared times I? Let's try that. What's I squared? -1, right? So isn't that just equal to negative I then? You see? Right? Yes?
So why is it I squared it? Why is it different?
Well, I'm just saying, what if I is actually being squared? What's that equal to?
Why would it be squared?
Well, because what if we were, okay, I'll tell you. What if we wanted to find, what we're going to do with these imaginary numbers, I shouldn't use the word complex here because I haven't talked about that yet, but if imaginary numbers, let's say we wanted to do some arithmetic with them. Okay, what if I wanted to add up, for example, 2i plus 3i? What do you suppose that answer is? We'll talk about it, but I bet you can tell me. What do you think it is? 5i, sure. Yeah. The I is just, I mean, those are sort of like terms in a way, aren't they? I've got 2 of these imaginary units plus 3 of these imaginary units, must be 5 of them. Yeah, it makes sense. Treat it like a variable, right? No big deal. Okay, but what if I take a product? 2i times 3i. That's a little different.
Wait, how did you get to 3?
I just made it up. Well, what if we want to do that? What if we want to add, we need to be able to work with these numbers. If we're going to do algebra that includes imaginary numbers, that's going to entail doing some arithmetic also, right? Arithmetic follows up. Arithmetic is one of the tools that we need to do algebra. So we got to know how to do this stuff. And there was a good question. Jennifer asked the question, why would we ever have an I squared? Well, we're going to here, aren't we? Right? Now, if I think about this product, I could divide this up into 4 separate factors. I've got a 2 times an I times a 3 times an I, right? And multiplication is commutative and associative. So we could rewrite this as 2 times 3 times I squared, right? 6, now what's I squared? -1, so our answer is -6. See what I'm saying?
Yeah, so why is I squared -1?
Because I is equal to the square root of -1, right? And so if I square both sides, that makes sense. So I squared equals the square root of -1 squared. A square root and a squared cancel, just leaving me with the -1. Okay? Strange. Strange that something squared could be negative, but remember, it's not a normal number. It's this new strange imaginary number. Okay? Questions so far?
Could you have an imaginary number of -1?
Well, very good question. Yeah, you can. There are other kinds of bizarre imaginary numbers too, but
-1 is equal to I.
yeah. Let me put it this way. Any imaginary number can always be written in terms of I. Let's just say that, right? So for example, this is kind of maybe a simple answer, but 3i is different than I, right? That's an imaginary number. Does that make sense?
I meant like.
Could you have like a j or something that's
Would you always write that like square root of 5, square root of -1
yes.
to make it?
Yep, exactly. Precisely. You can always take it and you can always simplify it so it's going to be some number times I.
So I would always be square root of
Yep. And what if you had something like, you're probably thinking, what if you had the square root, or like the 4th root of -1? Even the 4th root of -1, we could write in terms of i's. Okay? Good question. Yeah.
How do you use this in physics?
Well, I showed you an example, kind of. But for me to go into that, it's not going to do any good because you don't know the math yet. I mean, I can give you some, when we have time, I'll tell you some cool stuff you can do with it. But in order to get there, you got to learn this stuff first. Yeah.
So suppose there's the 2i times 3i,
Mhm.
and -6 would the -6 be imaginary?
No. The -6 ends up being a real number. Okay, now hold that thought though. It's a really good question. That seems weird. We took two imaginary numbers and multiplied them together and got a real number. Okay, it turns out that all of these together fall into a set of numbers called complex numbers that include both our normal real numbers that you've always dealt with and these new imaginary numbers. They all fall under the umbrella of something called a complex number. Okay, so we'll get to that. But that's a good question. These are all really good questions. Okay, so let's keep going then. So we said that I cubed we could write as negative I. What about I to the fourth? Now I to the fourth I could recombine as maybe just I squared times I squared, right? Agreed? Well, I squared is negative 1. So what's negative 1 times negative 1? 1. So I to the fourth is just 1, right? Okay, now this starts to get boring though, doesn't it? If I did something, question, yeah.
But there could be a problem, because like, 1 is a real number, so would they put like something, and then instead of putting 1, they put I to the fourth?
I to the fourth could, well, in the process of doing arithmetic, we might sometimes be asked to take a number to the, like an imaginary number to the fourth power.
What's the point of I to the fourth if it's already a real, why don't we just write?
Well, the simplified answer would be 1. You're right. You're right. Now, we're going to see some stuff. I know what you're thinking. That seems a little off, but when we start talking about the arithmetic of imaginary numbers, sometimes the imaginary numbers disappear completely. That happens, and we get real numbers. But I'm going to show you a way to compare both of those and represent both of those in a common way, in what's called the complex plane. And then I think it'll really make more sense. Yep.
Okay, so I cubed equals negative I, but I equals negative 1, so.
No, I equals the square root of negative 1.
Okay, so I
Right.
was thinking negative I squared root then.
Now, do you see why this is going to get pretty boring after this? If I could keep going indefinitely, but I to the fifth, what would be a really convenient way to break down I to the fifth? Okay, maybe even better than that. There's one that would be really easy up here to use.
Negative
I to the fourth is just 1, right?
I.
Does that make sense? So I to the fifth, if I write that as I to the fourth times I, well, I already know that's just 1 every time, right? So this is just equal to I. See what I'm saying?
What?
Right? I to the fifth just equals I. Because it's the same thing as I to the fourth, which is 1 times I. Right? You get it?
6 is gonna be I.
I squared, isn't it? Right? You see this pattern starting to pop out now? Oops. Okay, so I need to add something right here. So we'll just say this looks kind of weird, but I to the 1, of course, is anything to the 1 is just itself, right? Yes?
How much are we gonna have to use this year?
A ton. Yeah, a lot. Yeah.
So I squared equals.
And so then we know that I to the fifth equals I, what's I to the sixth? Well, isn't I to the sixth just the same thing as I to the fourth, which is 1 times I squared? Right?
Negative 1?
So that equals negative 1, right?
Oh.
I to the seventh would equal I to the fourth, which is 1 times I cubed. Well, I cubed is negative I, right? And then I to the eighth would be what? 1, yeah. Because it's just I to the fourth times I to the fourth. Okay? That pattern is going to repeat over and over and over again.
So like, how do you want to,
That's.
Yeah.
I to the ninth would be the same as I to the fifth.
I to the ninth would be the same as I to the fifth, which is just I. Yeah. Okay, so let me ask you this then. You tell me, what is I to the 117th?
Negative I. No, not negative
is it? Here's some different answers. How are you gonna get it? More importantly,
Divide by 4, like,
yeah, because every 4, your answer's gonna be 1, isn't it? So if you divide by 4, whatever the remainder is, that's how many beyond this row right here we're gonna go, isn't it? Does that make sense? So 4 goes into, 116 evenly, right? So then there'd be 1 left over, and so it's gonna fall into the same row as I to the 1, so the answer's I. Does that make sense? You see what we're doing?
That is so confusing.
Right? But doesn't that make sense
Wait,
that you
so
know
how do
that
we
it's...
answer? The question is, how do you want us to answer in terms of I?
so we're
Like
gonna,
one?
so we're going to be defined,
Say it again?
Did we just answer that with I?
Yeah,
so we're going to
I mean,
define,
no problem like that on
yeah. But that's an easy one to do. Whatever the power is, you just divide it by 4, and then whatever, ask what the remainder is when I divide it by 4. And that's the answer, right?
we're going to get a bunch of problems where I is going to equal like -2 or -3.
Yeah, you'll get some stuff like that. I mean, I'm not gonna load you down with a ton of those because they're not that big a deal. But our answer is, right, for larger exponents, just divide by 4 and apply the remainder. That's it, okay? So that'd be the same as 5 with remainder of 3, so it's same as I cubed, right? -1, or -I, sorry. Okay? All right, so moving on. Let's look at some arithmetic. What's that going to be? Now, we got to use some properties of exponents here that you haven't used in a while, but you know them. You guys are so good at arithmetic and algebra. If I take something like this, if I take something like a times b to the m, what can I do to that? What can I do to the exponent there? Yeah, I can distribute it effectively, can't I? I can
Yeah, so
rewrite that as
The
a
answer's
to the m.
negative.
Yeah, right, so we're gonna get, in this case, I'm gonna get the same thing as I squared times the square root of 3 squared. But what's the square root of 3 squared? 3. What's I squared? -1, right, exactly.
Is there an I button like on the calculator?
Yes, there is. Yes, there is. Good question. I'll show that to you. Yeah. I'm going to show you some good imaginary number stuff on the calculator too. I may not get through all this stuff today. And I'm probably, honestly, I'm probably taking longer with this with you guys than I would with maybe even just regular algebra 2, because I really, I mean, you're going to use this a lot more. I want you to really be familiar with these complex numbers. So, okay, well, we already did this one, didn't we? Is this one we did? Divided by 3, took a square root, and so we said then that we end up with plus or minus I times the square root of 12. Now, there's a really quick way to do this. You can automatically say that whenever you see a negative sign inside a square root, all you have to do is think of that as the square root of -1 times whatever the number is, right? And so you automatically know that this translates into an I times a normal square root.
So what if
Right.
you like simplify those into square root? It would be like I number and then the square root? Like do you still simplify what's inside the square root?
Correct. Yeah, exactly. Right. So then, yeah, how would you write that? Good question. So let's go a couple steps further. So the square root of 12 breaks up into 2 times the square root of 3, right? And so we would, the mathematicians, and they're really particular about these things, we would nest the I between the 2 and the square root of 3. Technically, the I, really, we think about it as being at the end. Okay. But we just don't put it there because of the ambiguity of is it inside the radical or not. It's just a little messy, right? Questions?
So,
Right. All we did was just took that square root of 12 and simplified it.
so basically instead of 4, it's
Yep. 2. Exactly. We factored out the biggest perfect square. Okay? Okay, so here's the part that's a little strange. So now, if you think about the set of all the numbers that you've ever dealt with, and I want to actually draw you a picture here to help you visualize this. If you look at number sets, all the stuff you've ever dealt with has been a real number. So if this whole thing right here, we're going to call the set of real numbers. There are all kinds of subsets that we've talked about. We talked about rational numbers and irrational numbers and integers and right. And we could review all that stuff, but you're good with that. Everything you've ever dealt with, though, has been a real number. Okay. Now we introduce this other set called the set of imaginary numbers. Imaginary numbers are numbers that can all be written. Well, in what form could I write all imaginary numbers? Okay, something times I, right? I could write them as a real number times I. Does that make sense? So all of these over here we could write as something like A, where A is just any real number. All of these over here we could write as B times I, where B is real, but I is that imaginary unit. Does that make sense? Okay. So then, what if I combine all of this stuff together into one big set? I can. It's called complex numbers. And all complex numbers are written in the form A plus BI, where A and B are elements of the set of real numbers. So A and B are real numbers. I is this weird imaginary unit, but all complex numbers can be written this way. Okay? You have dealt your whole life without knowing it with complex numbers, only the complex numbers you dealt with had a value of B that was 0. They never had an imaginary part to them. The imaginary part disappeared, and we were just left with the real part. But they still are a subset of this set of complex numbers.
Would that be simplified then?
It can't be simplified because this term, the imaginary part is multiplied by I, and the real part is not, and so those can't be combined. Okay, and that is, by the way, what we call the standard form for a complex number. Okay, is A plus BI, where A and B could be anything, square roots, pi, any real number is fair game for A and B. Okay, question? Yep. When you multiply a real number times I, it becomes imaginary. Right, for example, go back to our last example we just looked at. Right, we had, go back to this example right there, right? See, look, we got stumped because we had the square root of a negative number, right? We broke that up into the square root of 12 times I. The square root of 12 is real, isn't it? Right? Does that make sense? And so we've got this real number, 2 times the square root of 3 multiplied by I. That makes the answer imaginary because it's multiplied by I.
Okay, but on that one problem where it had like a negative 2I times the
Okay, now that's different. If I multiply a pure imaginary number times another pure imaginary number, then then it becomes real. Okay, but what's nice about that is they're all just complex anyway, right? So they all still fall under that umbrella of complex numbers. Okay. Now this will make it easier to visualize. Okay. So standard form is A plus BI. We say that the real part is the first term, the imaginary part is the second term, right? And an example would be 5 plus 4i, or 2 minus 3i, okay? So the complex plane knits both of these two sets together in one two-dimensional representation. The complex plane looks just like the xy plane, like the Cartesian plane, only instead of an x-axis and a y-axis, we have the real axis and the imaginary axis, okay? So what we do here, if we want to represent a number on the complex plane, we represent it as an ordered pair, where what used to be the x component is now the real part, and what used to be the y component is now the imaginary coefficient, so b, right? So for example, if I wanted to plot the complex number -2 plus 5i, what are gonna be the coordinates of that point in the complex plane? Yeah, -2, +5, so we go back 2 and up 5, right? And we could plot all of these. They're all gonna be in different places. There's the first one, right? Second one's gonna be over 2 and up 2, right? Agreed? Okay. Next one is over 4 and down 3, and et cetera, back 4 and down 3. Okay, now what's really cool about this, and I want you to, I hope you get excited about this, because this is amazing. I just want you to kind of know how much there is out there to go with this. This opens up a whole new world of relationships that we can explore. If we plot these complex numbers in the complex plane, notice that, for example, they all have different distances from the origin, right? Well, the distance from the origin, which is represented by absolute value bars, the book doesn't say this, but it's really called the modulus. The modulus of the number is really important. The modulus of the number has to do with the magnitude of that quantity. So in physics, for example, when you start talking about things like you're using these, I'll give you the example of impedances. So for different circuits, you're going to calculate these complex impedances that have to do with how much resistance there is to the flow of electricity through the circuit, right? Well, you're going to get answers that are going to be complex numbers. So they're going to have i's in them. But you need to be able to think about that in terms of a real amount. Is this complex impedance, for example, bigger than that one? In other words, does this circuit have more resistance to pushing current through it than this one does? So how do you make a direct comparison? Well, you just compare how far those points are away from the origin in the complex plane. In other words, how long would the vector be that represented those, right? I can think of each of these, like for example, this guy right here, this number -2 + 5i, I can write as a vector, just meaning an arrow, whose tail starts at the origin and the tip ends at the point. The length of that vector, which corresponds to the magnitude, tells us effectively what is the quantifiable numerical value associated with the resistance to pushing electricity through the circuit. Is that making sense, kind of? Get an idea why there'd be important for us to maybe be able to say, okay, it's complex, I can't count with it, but I need to know which, when I'm building this circuit, which one has the most impedance. That's how I can tell.
Would
Yep.
the origin still be 0, 0?
It is, the origin's still 0, 0.
Okay, if I were actually like have a value in the imaginary number, so wouldn't you multiply that with the 3 on 5?
Well, it does. I corresponds to 1 unit along that, right? So this is 3 times 1, because this is the imaginary axis. Actually, this is the real axis. That's the imaginary axis, right? So that's telling us how many units are we moving up or down that axis.
So that would mean that that would actually be different from this if we're, let's say, I would 2.
Right, exactly. But we don't want to set it up that way. We always want to set up math systems to be what we call unitary, where the basic value is 1. Okay? And these are concepts, you'll hear this stuff again, you'll think, oh, yeah, I remember that. Okay, so this, all right. So then, absolute value of a complex number. Really, but remember, this is a little hokey, really it's not absolute value. Technically it's modulus. Okay. So that's just the distance of the number from the origin, right? In the complex plane. Well, now, if you think about that, that's that's easy, right? That's just the hypotenuse of a right triangle, right? If I go back to, well, let's graph this one. Okay, if we take the complex number, -2 + 5i, I just want you to see this. I mean, this is nothing earth-shattering, but I just want you to make this connection in your mind. If this is the real axis and this is the complex axis, or the imaginary axis, where is that located, -2 + 5i? Joe, you getting this?
Yeah.
-2 + 5, so I just go back to up 5, so there's the point, right? And so that's the vector representation of that, right? If I want to find out what the length of that is, why not just break it up into a right triangle? I've got the vertical leg, and I've got the horizontal leg. Well, the horizontal leg has a length of what? 2. right? The vertical leg has a length of 5, so doesn't it make sense then that that's just the distance formula, right? See what I'm saying? Okay. So all it is, the modulus, or the absolute value, if you want to call it that, is just the square root of a squared plus b squared for any complex number. And that gives us a value so we can compare magnitudes, right? So square root of 29 is the sort of the size of that imaginary number, the modulus. Okay. How about that one? What's the length of that one? Okay, so that's a pure imaginary number, isn't it? Right? So if it's a pure imaginary number, it's easy. It's 6 is the length of that one, isn't it? Right? Doesn't that make sense? If I were to graph that one in the complex plane, isn't that one just right there? Right? It's right on the x-axis, or the y-axis. It used to be the y-axis, right? And so it's just 6. Now, if I apply the formula, of course, it's 6. It's just the square root of 0 squared plus negative 6 squared. Square root of 36, which is 6, right? Okay. If I take a pure real number, what's that equal to? 3. Yeah. In fact, isn't that the very same thing? What's that one? 4. Isn't that the same thing as an actual absolute value then? Right? How about that? Does that blow your mind? So an absolute value is just the modulus of a pure real number. That's all it is. Amazing, huh? Okay. All right, so which is closest to the origin? Actually, that one is. So this is a bigger complex number than that is because it's got a bigger modulus. Okay. Okay, adding and subtracting, dead simple. All you do with adding and subtracting, add like terms. Treat the i's just like variables. I don't even need to say any more. So in this case, what would we get for an answer? Yeah, 2 plus 5i, right? And now I wouldn't even need to go through these steps. Right? All you're doing is you're just treating the I like a variable and doing the same algebra you would normally do for like an x. Agreed? So no big deal. I just distribute the minus sign, add up like terms. For you guys, that's a piece of cake. I don't even need to worry about that. Adding up a whole bunch of them, no big deal. Just adding up multiple variables, right? Just combine like terms. Okay, we can skip through that. Now, what about multiplication? Okay, you treat the i's like variables, but watch this. If I distribute the I there, I treat the I like a variable, so I get a negative 3i minus I squared. But what do we do to the I squared? What's I squared equal to? Negative 1. So whenever you get an I squared, you just turn it into a negative 1. And that's our answer. Right? So the product of these two complex numbers is that complex number. Make sense? And we always want to write it in standard form, a plus bi, so the real part comes first. What's the value of a? What's the value of b? Negative 3. Just negative 3, right? B is just the number that's being multiplied by I, the complex coefficient, imaginary coefficient. Okay, what about that? Wouldn't I just FOIL it out like normal? But the I squared term, the I squared becomes a negative 1, right? So when I FOIL it out, I get that. I can combine like terms, right? And the I squared becomes a negative 1. So that ends up being a plus 6. So the moral of the story is you know right away that when I get an I squared, what's it really going to do to the sign of that term? Just change it. It's just like you cover it up and change the sign of the term, and that's all it does. Right? So we end up with negative 12 plus 6, so that's our answer. Right? Okay, what about dividing? This is the tricky one. Okay, so what do you do, and what I really wanted you to think about here, just ignore this part. What do we do if we're dividing those complex numbers? Now, division of complex numbers, this is similar to the way you think about about dividing like square roots. Remember the rule we had for square roots is we never wanted to have a stranded radical in the denominator, right? So we always multiply top and bottom by the stranded radical, right? Oh, man. Okay, we'll finish this up tomorrow, and then I'll have an assignment up for you, and we'll head to the lab tomorrow and practice. We're almost done.